In our discussion today, we'll look at, for level measurement, a different type. We're going to be using hydrostatic head. This is when we have a liquid substance inside of our tank. There's a certain amount of pressure that's applied to the outer edges of the tank itself. If we're looking at just a simple level measurement, and we're going to be using a differential pressure transmitter, and we're also using an open tank, a tank that's vented to atmosphere. And as we've seen on some of our other experiments, that when we have equal pressure applied to a differential pressure transmitter, that they cancel each other out. A DP transmitter is looking at just the differential pressures between the high side and the low side. So if we have atmospheric pressure applied to the low side or the high side of a DP cell, and we have that same amount of pressure applied to the low side, the net result is nothing. So there is no change in output due to those pressures canceling each other out. And as the liquid level goes up in a tank, what happens to the pressure exerted, and it could be here at the bottom on the side, it could be mounted somewhat above the bottom on the side of it, it could be mounted below the tank itself. It's still going to be a hydrostatic pressure. We are not measuring the weight of the substance that's in this tank. We're measuring the pressure that's being exerted to the side of the tank and to the bottom of the tank, something that is containing this liquid. And as this liquid level starts to go up, so does the hydrostatic pressure that's being applied at that one specific point in the tank. Now there's something we have to know. There's two things we have to know as we're determining what to calibrate our transmitter to, because we have to have it ranged for a certain amount of liquid height, the liquid change from 0% to 100%. We have to know that. We have to know where physically 0% is, and we have to know physically where 100% is. And we have to know that in something that's relatable to the gauges, the scaling of the gauges that we use to calibrate or to set up this transmitter for a certain application. Just to make things easier, we're going to go ahead and use 100 inches. Remember, I told you it's a physical height from 0 to 100%. So we have to know the physical height of this. The other thing we have to know is, what is the specific gravity of this liquid? What is it? We have to know that, and there's a reason why. Just what is the specific gravity? The reason we have to know that is because all of our calibration gauges in this room anyway are scaled in inches of water column. So we have to know the specific gravity to relate how much equivalence of this hydrostatic head being applied by this liquid is equal to the same amount in inches of water column. And then after we know that, it's a simple math formula to where we take specific gravity times our height is equal to whatever setting, whatever position we're looking at over here. If our specific gravity, let's just in this case, let's just make it a 1, is 1, and we're looking at 0% physically, if we have no difference in height physically from the tap on the side of the tank where we've actually drilled a hole into the side of the thing, to where 0% is, specific gravity being 1, height being 0 inches, that would be 0 inches of water column. Now if we go up here to a full level, we take our specific gravity, which is 1, and we multiply it by 100 inches, that equals out to 100 inches of water column pressure being exerted on the side of this tank where we have this located. And if we would calibrate it on the bench, we could go over there and we could apply 0 differential across here, across our transmitter, and set our 4 milliamps out if we're using electronic. If we're using pneumatic, we would set it up for 3 psi out, and we would apply 100 inches of water column pressure on the high side of the transmitter and set our range out. We would set it for 20 milliamps on electronic and 15 on a pneumatic transmitter. And it would be calibrated for this application. Now, specific gravity, let's go into that just a little bit. Specific gravity is a unitless number. It is the density of a substance, the density that would be in this tank, over the density of a standard. The standard in liquid measurement is water. So if we had something that was more dense in our tank compared to water, it would have a higher specific gravity. The specific gravity of water is 1. It's the standard. It's what everything else is referenced to. So if we have something that's a heavier density in the tank, it's going to have a higher specific gravity than 1. Not much. You're not going to see a specific gravity of 1,000. If you're going through your calculations, when you actually calculate what the specific gravity is, if you come up with a number like that, you need to go back and recheck your numbers. If we have something that's less dense than water, we're going to see a specific gravity less than 1. We think about, and here's an example for you, and this pertains to a liquid. If you're at the marina and you see an oil slick on the top of the water, that should indicate to you that oil itself is not as dense as the water because it actually floated on top of it. When we refer to a gas, air is the standard to it. A good reference to that one would be helium. Helium, if you have a helium balloon and you let go of it, it rises above the air. It floats above the air. So the helium itself is less dense than air itself. This is just a real simple thing. We have to know physical height. We have to determine specific gravity. And all we have to do then is multiply the two to get our calibration ranges. Now, this transmitter does not always have to be mounted at the side of the tank. It doesn't always have to be equal to the tank. For some reason, it could be mounted below the tank. We could have a leg that actually extends down somewhere and have our transmitter mounted below that. High side, low side, there's the transmitter itself, this is the sensor. We could have this scenario also, but if we do that and we have some liquid that's trapped or inside of this leg, and you should, we're going to have to account for that liquid level. It doesn't matter if this is 1/4 inch tubing or 3/8 tubing, which is very small, less than the size of this marker, or something the size of this tank. We're not measuring weight. We're measuring hydrostatic pressure. So that is not dependent on how large the container is. It's only dependent on the physical height and specific gravity. But being said, we have to account for this height. And if for some reason, well, we'll just pick out a number,